So let's say you had quadratic polynomial p of x, and you were given that p of 1 is equal to 5, p of 2 is equal to 11, and p of 3 is equal to 19. And you were asked to find p of 4. So in this case, most people would recognize that p of x is a quadratic, and that p of x is equal to ax squared plus bx plus c. So you would plug in the values of x, and you would plug in p of x to get a system of equations. So you would get that 5 p of 1 is equal to a plus b plus c. 11 is equal to 4a plus 2b plus c, since it's x squared. And 19 is equal to 9a plus 3b plus c. Then you would solve this system of equations for a, b, and c. You would find this quadratic equation, and then you would plug p of 4 in to find the answer, right? However, there's a much easier way to find this. So first, just write out the three terms, 5, 11, and 19, and find the difference between them. So the difference between these two is 6, the difference between these two is 8, and the difference between 6 and 8 is 2. So this process of finding the difference between the terms essentially reduces the polynomial into a lower form. So this quadratic turns into a linear, which just turns into a constant difference. So since this is a constant difference, well, it's constant. So the difference between this term and the next one here is also 2. So that means this is 10. So that means the difference between this term and the next one is 10. So this term here is 29. So p of 4 is equal to 29. We can also check using the system of equations, and if you solve this lengthy system of equations, you get that a is equal to 1, b is equal to 3, and c is equal to 1, giving the quadratic x squared plus 3x plus 1. If we were to plug in 4, you get 4 squared plus 3 times 4 plus 1, which is 29. The same exact thing. But you might be wondering how we would be able to solve other polynomials, like third degree, fourth degree, or even fifth degree. Well, this method works for those too. So let's say you were given a fourth degree polynomial p of x, such that p of 1 is equal to 1, p of 2 is equal to 2, p of 3 is equal to 3, p of 4 is equal to 4, p of 5 is equal to 125, and they were asking you to find p of 6. So if you were to use the system of equations method like here, you would have a system of 5 equations, and this would be pretty lengthy to solve. So if we use the previous method, we see that we can just put these in a line, 1, 2, 3, 4, 125, and just find the difference. So this is 1, 1, 1, 111, 0, 0, 110, 0, 110, and 110 is the difference. The constant difference, this is linear, this is the quadratic, this is the cubic, and this is our original quartic equation. So now that we know that the constant difference is 110, we can add 110 to this value here. So 110 makes this 220. Adding 220 to this term here gets us 330. Adding 330 to this term here gets us 441. And adding it to p of 5 gives us 606. So p of 6 is equal to 606. And if you don't believe me, you could make a system of equations using these 6 variables. Find a, b, c, d, and e in ax4 plus bx cubed plus cx squared plus dx plus e. Plug 6 into that equation, and you would get the exact same answer. So this technique works. It doesn't have to be p of 1, p of 2, p of 3. You could be given like p of 7, p of 8, and p of 9, and would be able to find p of 10 with this method. However, one important thing to note is that if you're given an nth degree polynomial, you need at least n plus 1 consecutive terms in order to find the next term. So if you're given a degree 2 polynomial, you need 3 terms. A degree 3 polynomial, 4 times. A degree 100 polynomial, 101 terms. But in not all scenarios will we have numbers listed out so nicely, like the p of 1, p of 2, p of 3. Well, this method also works for any 3 terms which have a constant difference in the x value. So if you were given p of 1, p of 1.5, and p of 2 for a quadratic equation, you would be able to find p of 2.5. Similarly, if you were given like p of 2, p of 5, p of 8, and p of 11 for a cubic equation, you would easily be able to find p of 14. All in all, this method is much, much easier than solving it the traditional way, and I hope this helps.